Okay, Matrix, welcome to your first video lesson with regards to fluvial geomorphology. You will see here there's a few videos for you that are added to help explain certain concepts with regards to stream patterns, stream orders, river, river capture, and then, how can I say, drainierdigtheid, your drainage density, the amount of streams, the hoeveelheid strome that is within a catchment area. What's a catchment area? That's an area where all the river streams flow into the mainstream, where it eventually goes to a mouth into the ocean or into another dam or lake. We'll get more into that later in the slideshow. You'll also see there's a video about the Holstrom curve down here and a flood hydrograph. The flood hydrograph we've done before in grade 10. This is just a recap of the flood hydrograph, and the Holstrom curve you will also find in your task. It's an easy curve, it's not very hard to understand. The whole graph goes about how big particles need to be, soil or rocks, versus how fast the water needs to flow to transport it away. So you can go look at these videos as an extra part to help you throughout the slideshow or when doing the task. Let's go on to our next slide. Drainage systems in South Africa. Drainage systems refer to, I'm at the first point there, drainage systems refer to a number of small streams and rivers joined to form a river system. A river is a body of water flowing downslope and is defined as a channel from a source to a mouth. So the source, where does the water come from, and the mouth, where does the water go out. Let me just try and do that a bit better. I'm not good with drawing on this. I'm used to having a laser pointer. Source and the mouth, where the river comes out. Then a drainage basin and a catchment area. The area drained by a river or a stream network is called the drainage basin. The catchment area is the drainage area that supplies water to a river. This water comes from the rainwater that flows downslope of the high ground, as well as from the underground water that seeps into the river. The area of land forming the catchment area of a river is not always the same size as the drainage basin, as it's determined by the origin of the underground water. So, what is a catchment area and a drainage basin? A drainage basin is an area drained by rivers or streams. A catchment area is the whole area that is drained by rivers or streams, as well as underground water. So, if the underground water comes from outside of the drainage basin, that means the catchment area can be bigger. As ek praat van ondergrondse water, when I'm talking about underground water, I'm talking about underground rivers, streams, aquifers, enige ietsie van waar ons water uit die grond uitpomp. Some of you have boreholes, boorgate at home that you can use, or that provides you some of this groundwater. Let's go on to our next slide. If we look at drainage systems in South Africa, drainage basin in KwaZulu-Natal, in this case it shows you some of the, let me just change the color here for this slide. This shows us some of the drainage basins in the area around KwaZulu-Natal and where they drain out into. We can clearly see that in this one, the biggest one will be the Utukela River drainage basin or catchment area. So this is the catchment boundary / watershed. That means this area here, this line running across here, is the line that creates a boundary. So all the water that falls on the right of this line will flow into this Utukela River. Anything falling to the left of this line will fall into the Umgeni River area. Okay, sorry about that. So, let's go to our next slide where we talk about drainage systems in South Africa, the precipitation that falls in a drainage basin. A drainage basin is an open system of inputs, stores, and flows. Now, inputs meaning our sources, stores meaning things like dams and lakes, damme en groter opvangsgebiede, and flows are rivers. as well as outputs where it mouths out into the ocean or into a dam. So these are the different parts that make up our drainage basin. The drainage basin collects precipitation, allows for water to infiltrate or seep underground to become groundwater, and stores water in lakes, in wetlands, and underground. Rainwater does not infiltrate underground flows. Oh, sorry, I'm wrong there. Rainwater that does not infiltrate underground flows over the surface as the surface runoff. So surface runoff, any water flowing over the top of the ground. This runoff flows into streams that join the main river that flows out of the basin. Eventually, this water flows into the ocean when the river reaches sea level. Precipitation does not infiltrate underground or flow over the surface. Flow over the surface may evaporate, be intercepted by vegetation, or be transpired as water vapor. Next slide. Features of a drainage basin: the high ground separating one drainage basin from the adjacent drainage basin is called the watershed. So that is like the top of a mountain. If the water falls down, the water will flow one side or the other side. Within the drainage basin, individual streams and rivers join together to form the stream or river network. The individual river channels that form the stream network are called tributaries. The confluence is the point where one river in a network joins another. Now, confluence, samevloeiing. Confluence meaning where all the streams flow together. Tributaries, sytake, meaning all the side channels of a river where the water flows into the main stream. They contribute to the main stream. That's why they're called tributaries. If you look at the features of a drainage basin, we have interfluves, tussenstrome. Interfluves or spurs are the ridges of high ground between individual channels of a stream network. Tussenstrome is die ribbel of hoëgrond tussen individuele kanale van 'n stroomnetwerk. So in other words, these are areas of high grounds in between the river network itself. The place where a stream or river begins is called the source of the stream or the river. This is usually in mountain terrain where the precipitation flowing over the land erodes small channels. Rivers can also rise at springs or where there is melting ice. Now, what's a spring? In other words, a spring is where we have the Earth's surface here. Let's say this is the side of a mountain. We have underground water flowing here on top of a hard plate of rock that it can't go through, and then it seeps through the surface on this side, allowing water to seep out of the surface and then create small channel networks. The river mouth is where we already discussed. Next slide. Features of a drainage basin. You can look at these images. This explains to us our watershed, our source, our spurs or interfluves in between the main channels, our confluence where they flow together, as well as a joining drainage basin. This line here, I wanted to ask you guys just now, what is this line called? But then I realized you guys are on the other side of a video and not in class with me. This is our watershed. This is the area, our watershed, between the different drainage basins. But what is the difference between a drainage basin and a catchment area? A catchment area can be bigger than a drainage basin because the source of the underground water can come from outside of the drainage basin itself. Let's look at drainage systems in South Africa. Important watersheds in South Africa. You can read through this: the Drakensberg Mountains, Witwatersrand, and the mountains of the escarpment. Now, where's our escarpment again? Remember, we get our coastal areas. Next to our coastal areas, we get the escarpment, our mountains areas, where we get the upper part of South Africa, the plateau where we are living. So what they're talking about, the escarpment, is a watershed as well. A lot of these slides I'm going to scroll through quickly because that's something you can read through on your own time. Remember, these slideshows are on Teams as well. You can go take a look on Teams and scroll through it on your own time. Let's take a look at surface runoff on groundwater. Large amounts of rainwater may flow over the surface as surface runoff or overland flow. It tells you what it is. It's overland flow. It's just flowing over the land, the surface. This surface runoff erodes small streams that eventually join together and forming wider, deeper channels in which water flows as channel flow. So firstly, we get overland flow, afloopwater that flows over the top, oor op die bokant van die oppervlak, and then canal fluid channel flow, where it channels into, that looks something more like a river. Then we also get something that's called through flow, deer fluid in other words. It is water that infiltrated in the earth's surface, in the ground, and now it's flowing through the ground particles underneath the ground. Water may percolate into permeable rock. Now, what does permeable rock mean? Let me just deurdringbare gesteentes. That means this is rock that water can go into and through. If it was impermeable rock, that means the water can't go through it. If it's permeable rock, that means there's holes in it so the water can pass through. Here's a little sketch for you guys about drainage systems in South Africa, Rivierstelsels in South Africa. We can see precipitation, the rain, evaporation taking water away, evapotranspiration by plants. Oh, yeah, no, that circle did not end well. Evapotranspiration by plants. We get channel flow in the forms of rivers. We get overland flow in the forms of water flowing down the surface of an area. We get infiltration where the water seeps into the ground. We get percolation where that circle also didn't end well. Percolation where the water seeps into what? Permeable rock. With this, we can get in the infiltration in the upper surface, loose ground particles, where we can get things like through flow. And what is our water table? Our water table is the area on top of which through flow will happen. I hope this sketch makes sense. I know I'm going through it quite quickly. Luckily, this is a video, so you can go back and you can play it again. We're only on slide 10 of 79, so there's a lot of things that still need to come. Like I said, the videos I'm not recording sound on now, you can go back and watch them again, and you can download the slideshow from Teams under class materials, if I remember correctly. It's river systems or Rivierstelsels, and you can go read through the slides. I tell you just to read through. This video will be way too long if I have to discuss each and every slide. I'm focusing on some key points for you guys. Drainage systems in South Africa. The following factors determine how much water becomes surface runoff and how much infiltrates underground. Relief, in other words, how steep is the area, the soil type. If the soil type is looser, more permeable, more water will flow through it. And the rock type. Like I said, impermeable rock means water can't flow through it. If it's permeable, the water can seep into it. Then drainage systems in South Africa. Again, we look at factors such as soil moisture, vegetation, plant rainfall, and land use. These are all things you can read through and you must know. These are factors that affect runoff. The more vegetation there is, the more grass, the less the runoff will be. What will have more runoff? A paved area, like a parking lot, or a rugby field, if they're both the same size. The parking lot will have more runoff because the water can't seep into the ground and there's no vegetation slowing down the amount of water that's flowing over it. Water table infiltrates the soil and percolates through the permeable rock underground. May come to a layer of impermeable rock where it can't seep through, which will prevent it from percolating further. You can read through that. The height of the water table varies with the seasons, being closer to the surface in the rainy season when there has been more infiltration. So, what is our water table? If we look at the underground, let's say here's the top of the ground, this is everything underground. Oh, rain falls, it percolates in. As it hits an impermeable layer of rock, the water level starts rising in this rock level because it's permeable. In other words, it has water in it. As this water layer rises, this is my water table. The top of the water level underground is my water table. So as there is more rain, my water table will rise. Here you'll see a little image of that. Let me just see to the next slide. Okay, so now we can see on this slide rather, dry season, wet season. The zone of saturation, aka the water table. This line here is the top of my water table. The zone of saturation, versadigingszone, is where my water table is in the wet season. We can see it's nice and high. That's why the springs to the top of the hill are coming out. And the river that flows there has water in it because the water is seeping through into this river. In the dry season, we can see this water table is very low. And there is no water in the river, no springs visible. Drainage systems in South Africa, types of rivers. We get a lot of types of rivers. Let's go through, because I think the side water infiltrates the soil and percolates through the permeable rock. This is discussing water tables again. I just want to go back one slide. I can't go back one slide. The types of rivers that we find, the previous slide was a copy of the one before it, sorry about that. The types of rivers we find is permanent rivers and non-permanent rivers and perennial rivers. Now what's the difference? These are things we've discussed before. Permanent rivers will flow throughout the year. Non-permanent rivers or perennial rivers, in other words, they will only flow at certain times of the year. They're seasonal. And then we get exotic rivers that flows through areas that aren't characterized by water flowing there. And lastly, we get episodic rivers as well that will only flow when there are heavy spells of rainfall, for example. You can read through these slides on your own time. Again, it is also explained in the textbook and in the videos. Periodic rivers, episodic rivers, and exotic rivers. Drainage pattern, again, falling back on the definition of a drainage pattern. The drainage pattern refers to the way in which the river within a river system or networks are arranged. Most patterns that developed are related to the geology or the topography of the area. So what they're telling us is, what hulle vir ons sê is, that die rivierstroom, the river streams that flows in an area, flows in that way because of the topography or the geology of the area. What is meant by geology? By geologie? The soil type and the rock type. Is the rock type easily eroded or not? The topography, is it steep inclines? What is the relief of the area? So the geology and topography both influence the pattern of our drainage area. We can see here, these are just a quick few examples where we get parallel, dendritic, radial, rectangular, deranged, centripetal, and trellis. In the following slides, they will go into more detail why it's called this. The only thing I want to point out on this side is if you look at radial, you'll see the center point is the highest point. So the highest point is in the center and the water is flowing outward from the center. So you can just look at that. And then the next slides I will just scan through quickly. You can read more on that later on. Okay, sorry about that. Phone calls in between. Let's continue. Drainage systems in South Africa. Here we can see the radial and the rectangular drainage pattern, explanation of each of that. The trellis, the centripetal, you can read through that on our normal slideshow. Just for you that can't find these slides, you can, this specific slide I'm on now is slide 24. So the previous one was 23, this is 24. 25 we can see dendritic, parallel, deranged, and we can also see an explanation of drainage density and factors that influence drainage density. These you can read through on your own time. This is slide 26. Here we talk about drainage density again, where we can see a low drainage density and high drainage density and extremely high drainage density. The more little streams there is in a drainage basin, the faster it will drain away water. So if the water falls down and there's more streams, there's more water that can be drained away. If there's less streams, there's less water. So what can we also see about this? If there's an extremely high drainage density, that means that's an area that receives a lot of rainfall. If there's a low drainage density, it's an area that receives less rainfall. So what can we say? The one with the extremely high drainage density will be in places like KwaZulu-Natal, that is a subtropical area that receives a lot of rainfall, and places with low drainage density is areas such as the Northern Cape that will receive less rainfall. And yes, I'm recording this at school on the 24th of March, the day before no one is longer allowed at school. I wanted to do this on the whiteboard for you guys and sketch it out, but unfortunately due to the news we received last night about the lockdown, that's not going to happen. That's why I'm doing it like this. Luckily I can figure these sort of things out on my computer. Let's look at the stream order. This is very important. Your stream order plays a big part in the bifurcation ratio. Now, don't stress too much about the bifurcation ratio just now. There is extra work that I sent to your tablet. Okay, sorry about that. I'm sitting at reception at the primary school. So, stream order is very important with regards to bifurcation ratio. Now, bifurcation ratio, I'll explain in more detail. I'll do examples with you on the board in class on how to calculate it. I also have extra resources that I will give to you with regards to bifurcation ratio that explains it a bit better. Now, the only thing you need to know for stream orders about now is how to calculate stream orders. Hoe om te bepaal wat is die stroomorde van 'n rivier. This is important for the task that you will be receiving. So let's look at this map down below. We can see first order streams are our smaller streams. Now, two first order streams that flow into each other will create a second order stream. Two second order streams flowing into each other will create a third order stream. Now, if a third order stream and a second order stream flows into each other, it will stay the highest order. Same here, a third order and a second order stream flowing into each other, it will stay the highest order. The only time this will change is if there is third order streams flowing into each other, and this will be the fourth. So let's take a look to this area on the right hand side. Let's try and calculate. So we get a first order, a first order, a first order, a first order, all these first order streams here to the sides. Let me just number them. Now all these first order streams, where they flow together, we get a second order stream. So here's another second order stream. Yeah, it's hard to draw with this mouse. Here's another second order stream. Here's another second order stream. Here's another second order stream. And another second order stream. So where the two second order streams flow together, we get a third order. We get here two second order streams flowing together. We get a third order, two second order streams flowing together. We stay a third order. So that means down here is a two third order streams flowing together. That will be a fourth order, and a third order flowing into each other. So that means at X, at the mouth of the river, it will be a fourth order stream. If you're struggling with this, don't hesitate to send me a WhatsApp. Please try and keep it within class times. With regards to after 8 in the mornings, before 12, if you have to after 12, it's fine. After 2 in the afternoon, it's fine. Just try and keep it before 6 at night. Please, please, please. And then let's continue to our next slide. Discharge of a river. What is discharge? Afloop. That is just the water flowing out of the river, the amount of water that flows past a specific point. Afloop is die hoeveelheid water wat verby 'n spesifieke punt vloei op daai stadium. You can look at that. That will be our COMEX or CHEMEX on our hydrograph. You can watch the video about hydrograph again where it explains what is a hydrograph. If you're struggling with the concept, there is not a hydrograph in your task. We will then look at hydrographs and bifurcation ratio when we all get back. If it takes a bit longer, then I'll make videos for you guys explaining hydrographs and bifurcation ratio now. At this stage, I just want to buy us some time. So let's see, discharge of a river, you can read through that, the nature of flow. Now it talks here about laminar flow and turbulent flow. Now, laminar flow being a smooth flow of water. Turbulent flow being choppy water, water that is like whitewater rapids. Why would it be laminar or turbulent? Laminar meaning it's a smooth river bottom, so the water can flow smoothly over it. Turbulent meaning it's a rocky river bottom, so the water will flow turbulently over it. It will create things like white waters and rapids. You can see here where it talks about laminar flow. You can read through that on your own time. Turbulent flow, you can read through that as well. This is something we've discussed before. We've discussed that in a cross section of a river like this is, remember cross section meaning side view, that the center of the river is where we will have the greatest velocity. The fastest flowing water will be in the center of the river. If you have ever stood next to a river and you just look at the sides of the river, you can usually see the water's flowing slower there, it's a lot gentler. The fastest part of the river is usually in the middle of the river where we will find the deepest point because it's the most water that can gain the most momentum. Afrikaans, ek hoop julle bly nog by, as julle nie bly nie, asseblief sê net vir my, ons is nou op slide 23, min of meer wat ek besig was om te verduidelik, dan sal ek het weer herhaal in Afrikaans. Okay. Here we can see a river meander. This is something you've sketched multiple times. I don't really feel that it's necessary to explain this again. You can go read through river meanders. You can look at sketches online as well about river meanders. This is something we've been doing since grade 10, and I put the first sketch of a river meander in your grade 9 tasks. Okay. Let's look at the fluvial processes, the longitudinal profile of a river. What is a longitudinal profile? That means a side view of the whole river. So what we're looking at here, and this is also something we've discussed briefly in grade 10, we're looking at the upper course, the middle course, and the lower course of a river. Now, in the upper course, we have the two, well, in the upper, middle, and lower course, we have the two different types of erosion. We have vertical erosion en horizontal erosion. Ons het vertikale erosie en horizontale erosie. If we look at the upper course, we have more vertical erosion and less horizontal erosion. That's why it looks like a sharp V, because the water is flowing fast. It has a lot of energy. In the middle course, it starts to even out, so we get a shallower V. So we get more horizontal and vertical erosion. It starts to equal out because the water is now flowing slower, the gradient isn't that steep. Now we move down to the lower course of the river. The lower course of the river, this is just where it's about to mouth out into the ocean. So in other words, the water is now flowing a lot slower and it's not that steep. So at this stage it will look something like this on screen. It will be a wide, shallow channel. Not very deep, where the water flows out into things like deltas, tributaries, and mouths out into the river. The upper course, the steeper upstream, downstream, towards the mouth, the changes in gradient along the course of the river. I've discussed all this. You can read through this slide on your own time. We look here at fluvial processes, the transverse profile of a river. The dwarsprofiel. What is a transverse profile of a river? It is a side view of a river. You need to know this. They're going to probably ask you to sketch a side view of a river somewhere down the line, be it in map work paper 2. Well, it will most probably be in your map work paper 2. A transverse profile is of a river is also known as a cross profile of a river. This is drawn transversely across the river valley at right angles to the river and shows the shape of the valley. So they're not going to give you a line from point A to point B. They're going to tell you at this place in the river, sketch a transverse profile. Then you have to draw your own line through the river where you say at 90 degrees to the flow of the river. This will be your transverse profile. Here's just more on the sketches I made on the previous slide for you. You can read through that as well. Rapids, waterfalls, and fluvial landforms. These are all things I've explained the concepts already. These are things you can read through. If there's any questions, please don't hesitate to ask. This is slide 38 we are on now. Rapids, these form when a river flows over resistant layers of rock. Waterfalls, this is when a river crosses a horizontal or vertical layer of resistant rock. I'll get more into waterfalls when we get to the image. Headward erosion or terugsnijdende erosie is the river lengthens its course by cutting back upstream above its original course in the process. So remember that when we get to the image of that. Then the river erodes vertically, creating a narrow, steep-sided V-valley. This is now on our upper course. The chief erosion process is hydraulic action and abrasion. What is hydraulic action? It is the force of the flowing water loosening pebbles, stones, and silt from the sides and the bed of the channel, causing it to erode quicker. It's fast water, flowing very fast. Most of the erosion in the upper course of rivers occurs when the river is in flood. The river is able to carry eroded material in suspension downwards down the river. Then traction is when boulders and large rocks are pushed and rolled against the riverbed. Smaller rocks and stones are bounced along the riverbed in the process called saltation. Suspension is when fine particles stay suspended in the water. Just know these key concepts, know the definition of it. It's not a difficult concept to understand. Traction, bodemvraag, big rocks, saltation, smaller rocks, suspension, super small particles like dust, silt, sand. Here we're talking about formation of rapids again. The different types of waterfalls that can form due to the different types of rock strata, resistant rock. So this is an area of rock that is resistant to erosion. The lighter color brown is not resistant to erosion, so that's why the water is cutting away at it. More fluvial landforms, river meanders and alluvial fans. I'll show you a bit about alluvial fans when we get to that image. This you can read through at your own time. A mass movement we've done in grade 10, we've revised in grade 11. Sheet flow or platvloei is when water flows over a thin flat plate or hard surface. Then meanders we've done before, alluvial fans I'll show you on the image now. This is our meanders. Remember, the river takes the area of least resistance. Now if we look at this image, what will we get when the water starts flowing through here? I chose another color. Why is it still red? Blue. What will we get if the water starts flowing through here on the map? So the river will then flow from there to there in this area. This will be called a oxbow lake, a hoefystermeer, yes. And alluvial fan is what we can see here. We can see the water flowing down from the melting ice into very soft rock, creating a fan-like order of streams flowing down into this area. This is an alluvial fan where it's extremely soft soil and a multitude of different streams flowing in the area. More fluvial landforms, levees, braided streams, river meanders, and oxbow lakes form a wide flat floodplain in areas of little relief. So little relief, small to little gradient. The river channel in this stage has increased in size to hold the extra water that tributaries have added to the main stream. As the volume increases, the river can carry large amounts of material in a solution and suspension. The suspended particles are smaller in size and they may erode the channel laterally through abrasion. So you can read through this on your own time. We're talking about floodplain, so this is close to the bottom of a river. They say the fertile silt. This is an important term. The fertile, oh, my lines on this thing. The fertile silt deposited by the river is called alluvium. That is this soft, salty soil that we could see at the alluvial fan as well as in this area directly next to the river. This is our levees. This is an area of high ground that creates a sort of dam wall around it. You can look at a lot of different places in the world where they will find levees to block the high tide of the ocean because people start building below the high tide mark due to overpopulation or a multitude of different reasons. Braided streams, this will be in your task. You can use this sketch as well in your task. Meanders, I've explained this before. Oxbow lakes, we've done this multitude of times. This is how our oxbow lake forms. Step-by-step instructions. It's an easy concept. It's things that we've been doing since grade 10. I've asked this in a test before that you had to give me an explanation of how the oxbow lakes form. Here's some more fluvial landforms, deltas and deltas. So this area here, this is our delta, where the river flow mouths out into the ocean. Deposition near the mouth can result in landforms called deltas. Large rivers that transport much material slow down as they enter a lake or the sea. As a result, the deposited material, if the lake or sea are relatively shallow and calm, the deposited material builds up and extends into the sea or the lake, forming a delta. Okay, this specific one you see down here is from the Nile River. River gradings, this is important. You need to remember, this was asked before. You need to remember what's the difference between a graded and a ungraded river. So, if a river is termed graded, when a balance has been achieved between the gradient, the volume, the channel shape, so that the river has sufficient energy to flow. So a graded river has the energy to flow due to its gradient being steep enough, there being enough volume in terms of water in the river, and the shape of the channel allowing it to flow. The ideal longitudinal profile of a graded river is concave in shape due to the steeper gradient in the upper course and more gradual gradient in the lower course. A river in its upper course has smaller volume and uneven bed and turbulent flow. Turbulent flow contributes to the river losing energy. If it's smooth sailing, the water will flow easily and there's less energy needed for it to flow. An overgraded river is rivers flowing down a steep gradient or rivers with little friction because they have a large volume or an even bed. They have a great deal of energy, therefore they can carry a heavy load and flow quickly. These rivers are termed overgraded as they have excess energy. And then we get our undergraded river. Undergraded, the volume decreases or the gradient lessens, it's not as steep anymore, or the friction increases, there's more rocks at the bottom of the river. The river is undergraded and does not have enough energy to flow and to transport its load. So everything that was in the water when it becomes an undergraded river will settle down to the bottom because it has no energy to flow. It will be almost stationary. This is slide 56. The rejuvenation of river, you can read through the rejuvenation of rivers and how that happens. The only thing I will go through with you here is the permanent base level of a river is altered when isostatic uplift, isostatische opheffing. So this is when the earth surface rises, so it creates a sort of a break in it, or a drop in sea level. So either the earth's surface rises, or here where the sea was hitting the land, the sea level drops. So now it's here. So now it creates this uplifted area. On that area, the term where the low and high point meet will be the neck point, and the carrying capacity talking about the amount of solids or particles or silt being carried in the water. So if we look at the if we look at the rejuvenation of a river, we can see the potential graded profile here. We can see the nick point here, and the active vertical erosion, it's eroding away. So let's just clear this image. It's eroding away slowly but surely, cutting away into this area until it is a level flow again. So there's no more turbulence or anything hindering the flow of the water to the sea level. Rejuvenation of rivers, you can read through here further. Before rejuvenation, after rejuvenation. So before rejuvenation, we can see the floodplain, we can see the river flowing. After rejuvenation, we can see now that the river has seeped or lowered itself down into, it has increased vertical erosion, it has created terrace. What's a terrace? It's a step. That's our terrace within a valley. So creating essentially a small valley within a valley. The rejuvenation of rivers, Rivierverjonging, the increased vertical erosion where we had an old valley, we now have a new valley. River capture and river capture, stream capture. A river that flows down a steeper gradient or has a larger volume, or that flows over weaker strata. Now what's weaker strata? Again, strata meaning soil layer, weaker, softer, so it will erode easier, has more energy, and can become the captive stream. So we want to capture a stream. Refer to the figure on the next slide, we'll get to that now. Through headward erosion, so that's backwards erosion, cutting into it, the more energetic the river erodes through the watershed at X and captures the water of the less energetic river, which is flowing at a lower lying river. The discharge of the captor river increases, which gives it an increase in energy and rejuvenates the river, enabling it to erode vertically. So let's look at this one. We can see headwards erosion, so the river is flowing down this way, but it's cutting into this area, so it's going to capture the stream flowing up here. So this is my captor stream. So this is my captured river. This is the elbow of capture where it took over. This is the misfit. We don't want this anymore. This is the one we're not looking at. And this is my captor, the one that captured the stream. My roof, hy die roof gepleeg, hy die stroom gesteel. You can read through the different definitions of each one here. So that was slide 64, 65, superimposed rivers. Read through the definitions of this. They tend not to ask this. We will discuss it a bit in class as well when we're doing revision, but this is something you read through. Slide 65, take the time, summarize the slide for yourself. And then the surface is removed through erosion. This is now explaining superimposed streams. So in other words, there's a hard rock layer below it. There we can see by the darker brown color, the river is flowing. As the top gets eroded away, the river sinks down, and then it starts flowing through, cutting its path through. So it's superimposed, it's pressed into that harder rock layer. You can see an image of that. Then we get descended drainage patterns. Occurs when a river develops its course before the high-lying area was formed. After the river formed, warping, folding, and faulting occurred, and the rate of the down cutting by the river was greater than the rate of the uplift. So what they're saying is, at a fault line or somewhere, the Earth's surface started lifting up, but it was lifting up slower than the river could cut into it. That's what created this type of river. So in this type of river, the river's erosion is faster than the upliftment of the Earth's surface. Slide 70. Although about 70% of the Earth's surface is covered by water, only 2% of the Earth's water is fresh water suitable for human use. The fresh water supplies come from rivers, dams, and groundwater. Now, from here on, Most of this is management strategies, water scarce countries, how to manage water, how we're going to use water, how we're going to save our catchment areas. So through this you can read on your own time. I will just scroll through it and see if there's anything I need to explain to you still. We've already been 44 minutes into this slideshow. That's why I said this slideshow is supposed to take us about 3 to 4 periods to finish, because I'm brushing over it. The bifurcation ratio and Hillstrom curve will take a period all on its own. Like I said, we'll see what happens. If I see you guys on the 16th, 17th, the school will let you know about everything. By the time this has been recorded, I haven't heard anything yet. I do want to motivate you guys to finish your tasks before you get back to school, to do the IB exams and to use the memos and to mark the tasks, please. Let's scroll through these last few slides. Freshwater, clean water side 71, you can read through that. 72, you can read through that. 73, you can read through that. 74, 75, 76, 77, and that's the last of the sideshows. Good luck to you guys. I will see you again when school starts.